October 25, 1944. Leyte Gulf, Philippines. Lieutenant Commander Ernest Evans gripped the bridge rail of the destroyer USS Johnston as 17 Japanese dive bombers screamed down through scattered clouds toward his ship and the escort carriers she protected. The morning sun glinted off polished aluminum wings as the Aichi-D-3A Val bombers committed to their attack runs, diving at angles that would have made them nearly impossible targets just 18 months earlier. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Evans watched his gunners track the lead aircraft through the sights of Johnston's twin 5-inch 38 caliber guns. No frantic calculations of lead time. No desperate attempts to predict where a maneuvering target would be in 20 seconds. The shells his gunners were about to fire carried their own intelligence, their own ability to sense when death was close enough to strike. The first salvo thundered from Mount 51. 2 shells arced upward, their proximity fuses activated by the centrifugal force of launch. At 1,500 feet altitude, radio waves pulsed outward from miniature transmitters no larger than a man's thumb. When the reflected signals indicated the proper distance, electronic circuits closed with mechanical precision. Both shells detonated simultaneously, bracketing the lead Val in a cone of hot steel fragments. The Japanese aircraft disintegrated instantly. Its pilot never understood what had killed him. Neither did the pilots following behind, who watched their leader's aircraft simply vanish in a burst of flame and debris without any visible shell impact. The second Val pulled into a desperate evasive turn, but Johnston's guns were already tracking, already firing. Another proximity-fused shell exploded 20 feet from the aircraft's port wing. Shrapnel shredded control surfaces and punctured fuel lines. The bomber tumbled toward the sea, trailing black smoke. In 90 seconds, Johnston's 5-inch battery had destroyed 5 Japanese aircraft with just 12 rounds fired. The mathematical impossible had become tactical reality. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What Lieutenant Commander Evans witnessed that morning represented the culmination of 3 years of desperate innovation, brilliant engineering, and industrial mobilization that transformed American destroyers from vulnerable escorts into lethal anti-aircraft platforms. The proximity fuse, officially designated the Mark 32 variable time fuse, had turned the 5-inch 38 caliber gun from a weapon that required perfect prediction to hit aerial targets into a system that could destroy maneuvering aircraft with near certainty. The transformation began not with technological breakthrough, but with tactical catastrophe. December 7, 1941, Pearl Harbor, territory of Hawaii. As Japanese aircraft swarmed over Battleship Row, American destroyers fought back with everything available. The destroyer USS Ward had actually fired the first American shots of the Pacific War at 06:45 hours, engaging a Japanese midget submarine attempting to penetrate the harbor. But when the aerial attack began at 07:55 hours, Ward and every other American warship faced a problem that had plagued naval gunners since aircraft first became weapons of war. Their 5-inch guns required manual fuse setting for each round. A sailor turned a wrench against a mechanical timer while enemy dive bombers screamed down through defensive fire. Most shells exploded harmlessly in empty sky, their preset timers detonating seconds too early or too late. The destroyer USS Selfridge, moored at East Loch, fired 47 5-inch rounds during the attack. Her gunners achieved no confirmed kills against aircraft that passed directly overhead. The destroyer USS Blue expended 31 rounds with similar results. The mathematics were unforgiving and consistent across the Pacific Fleet. Traditional anti-aircraft fire achieved kill rates of approximately 0.04% under combat conditions. This meant that a single destroyer, carrying a maximum of 300 rounds of 5-inch ammunition, could theoretically engage targets for hours without achieving a single kill. The problem was not accuracy in the conventional sense. American fire control systems could track targets and predict intercept points with reasonable precision. The fundamental challenge was time fuses, which required perfect prediction of an aircraft's future position 15 to 30 seconds in advance. A Japanese VAL dive bomber approaching at 300 miles per hour could change course, altitude, or speed multiple times during those crucial seconds. Each maneuver made the preset time fuse worthless. Even if calculations were perfect at the moment of firing, any evasive action by the target meant the shell would explode in empty space, while the aircraft flew through the void where defensive fire should have been. The tactical implications were stark. Japanese aircraft could attack American ships with virtual impunity, facing defensive fire that was more psychological than physical threat. Dive bombers could approach methodically, select optimal attack angles, and release ordnance with precision, while ship-based gunners fired frantically at positions where targets had been rather than where they would be. The Battle of the Coral Sea, in early May 1942, illustrated the problem with brutal clarity. The aircraft carrier USS Lexington, escorted by destroyers USS Phelps, Dewey, Farragut, Aylwin, and Monaghan, came under attack by 18 Japanese Nakajima B 5N Kate torpedo bombers approaching at wave-top altitude. The escorting destroyers fired over 200 rounds of 5-inch ammunition during a 20-minute engagement. They achieved 2 confirmed kills and 3 probable kills against aircraft flying predictable approach patterns at consistent altitude and speed. Against the most favorable targets possible, experienced American gunners achieved a kill rate of approximately 2.5%. When the same destroyers faced dive bombers during the attack on USS Yorktown 2 days later, kill rates dropped to near zero as maneuvering targets made time fuse prediction impossible. Captain Frederick Sherman, commanding Lexington, wrote in his action report that defensive anti-aircraft fire was proving inadequate against determined aerial attack. He noted that destroyers were expending their entire ammunition allowance without achieving kills proportional to rounds fired. Sherman recommended investigation of alternative fuse mechanisms, though he had no specific solution to propose. The Bureau of Ordnance had reached the same conclusion through statistical analysis of combat reports throughout 1942. Admiral William Blandy, chief of the Bureau of Ordnance, received data showing that American destroyers were firing an average of 2,500 rounds of 5-inch ammunition for each confirmed aircraft kill. At that rate, a destroyer division could engage a single squadron of attacking aircraft and exhaust their combined ammunition supply without stopping the attack. The crisis was not just tactical but strategic. American naval strategy in the Pacific required carrier task forces to advance westward across thousands of miles of ocean dominated by land-based Japanese aircraft. Carriers provided offensive capability, but destroyers provided close-in defense against aerial attack. If destroyers could not effectively engage attacking aircraft, carrier operations became unsustainable. Admiral Chester Nimitz, Commander-in-Chief Pacific Fleet, identified destroyer anti-aircraft effectiveness as a critical weakness in a classified assessment dated August 15, 1942. Nimitz noted that Japanese aerial tactics were evolving to exploit American defensive limitations. Coordinated attacks using multiple approach vectors overwhelmed time fuse-based fire control systems that could not engage multiple maneuvering targets simultaneously. The solution emerged from a research program that had begun before Pearl Harbor, driven by British recognition of the same fundamental problem. The Tizard mission, which brought British scientific secrets to America in September 1940, included preliminary research on radio-based proximity fuses. British scientists had developed theoretical designs, but lacked the industrial capacity for mass production. Dr. Merle Tuve at the Carnegie Institution of Washington received the British research in October 1940 and immediately recognized its potential. Working with the National Defense Research Committee, Tuve assembled a team of physicists and engineers to develop what became Section T, the Proximity Fuse Development Program. The concept was elegant in theory, nearly impossible in practice. A miniature radio transmitter installed in the nose of a 5-inch shell would broadcast continuous signals. As the shell approached a target, radio waves would reflect back with frequency shifts caused by the Doppler effect. When the frequency shift indicated optimal proximity to the target, an electronic circuit would trigger detonation. This eliminated the need for time prediction. The shell would detonate automatically when close enough to the target, regardless of evasive maneuvers. A maneuvering aircraft would still reflect radio energy. The proximity fuse would still detect approach and trigger at optimal range. The system was self-correcting in ways that time fuses could never achieve. The engineering challenges were staggering. Every component had to fit inside a space 8 inches long and 2 inches in diameter. The radio transmitter, receiver, amplifier, frequency detector, power source, safety mechanisms, and detonator occupied the same volume as a 20mm shell. More daunting, every component had to survive the acceleration forces of gun launch. When a 5-inch shell is fired, it accelerates from 0 to 2,600 feet per second in approximately 20 feet of gun barrel. This creates acceleration forces 20,000 times greater than Earth's gravity. At 20,000 g, a 1-ounce component weighs 1,250 pounds for the fraction of a second it takes the shell to travel down the barrel. Standard vacuum tubes, the only electronic amplifying devices available in 1940, were fragile glass envelopes containing delicate filaments and electrodes. Commercial radio tubes designed for home receivers were 6 inches tall and weighed several ounces. Military tubes designed for mobile equipment could survive 10 g of acceleration. The proximity fuse required tubes that could survive 20,000 g while maintaining electronic function. James Van Allen, a young physicist who joined the Applied Physics Laboratory in April 1942, led the development of what engineers called ruggedized vacuum tubes. Working with Sylvania Electric Products, Van Allen redesigned tubes from fundamental principles. Glass envelopes were thickened and specially annealed. Internal components were shortened and reinforced. Electrode structures used spot welding techniques that created mechanical bonds capable of surviving extreme stress. The development process required thousands of test firings at the Dahlgren Naval Proving Ground in Virginia. Prototype fuses were loaded into 5-inch shells and fired from a vertical gun into soft earth that allowed recovery for examination. Engineers used microscopes to study fractured components, analyzing failure modes and redesigning accordingly. By September 1941, after hundreds of design iterations, acceptable tubes emerged from production lines. They measured less than 1 inch in height and could survive 20,000 g acceleration while maintaining electronic function. Success rates climbed above 50%, sufficient for the Navy to authorize production tooling despite continued reliability concerns. The power source presented equally complex challenges. Conventional batteries were too large and had limited shelf life in tropical conditions. Harry Diamond at the National Bureau of Standards developed an ingenious solution using a reserve battery design. A glass tube filled with electrolyte solution was sealed with metal plates at each end. When the shell was at rest, liquid remained in the center, isolated from the metal contacts. When fired, centrifugal force from the shell's rotation pressed the electrolyte outward against metal strips embedded in the tube walls. Chemical reaction between electrolyte and metal generated electrical current. The battery activated only when the shell was spinning, providing built-in safety that prevented premature detonation while ensuring power when needed. Multiple safety mechanisms protected against accidental triggering. The fuse could not arm until well clear of the firing ship. Wave suppression circuitry prevented premature detonation when shells were fired at low angles over water. Radio frequency filters blocked interference from the ship's own radar systems. Each safety feature added complexity, but combat conditions demanded absolute reliability. By June 1942, complete proximity fuses contained approximately 130 miniaturized electronic components assembled in a package weighing just over 2 pounds. The Mark 32 fuse for the 5-inch 38 caliber gun represented perhaps the most sophisticated piece of miniaturized electronics that existed in 1942. Production contracts expanded rapidly as combat reports documented the inadequacy of time fuses. The Applied Physics Laboratory at Johns Hopkins University, established specifically to coordinate proximity fuse development, worked with 5 major contractors: Crosley Corporation, Radio Corporation of America, Eastman Kodak, General Electric, and McQuay Norris. Over 100 factories ultimately participated in component production. The goal was 40,000 fuses per day by late 1943, rising to 70,000 per day by war's end. Each fuse cost approximately $18 in mass production. Expensive compared to conventional time fuses, but cost-effective given the dramatic improvement in kill probability. Security surrounding the proximity fuse was absolute. The device received the deliberately misleading designation, variable time fuse, to disguise its true nature. Workers assembling components never knew the final product's purpose. Different companies manufactured different subassemblies. Even military personnel using the fuses were initially told only that they were advanced time fuses with improved reliability. The first combat tests occurred in the Solomon Islands during early 1943. The light cruiser USS Helena received 500 rounds of proximity-fused 5-inch ammunition, with strict instructions that fuses were to be used only over water, where duds would sink beyond enemy recovery. Initial fleet reaction ranged from skepticism to curiosity about shells that supposedly set their own timing. January 5, 1943, off Guadalcanal, changed everything. 4. Japanese Aichi D. 3. A dive bombers attacked a U.S. Navy task force. As the aircraft broke off their attack runs, the cruiser Helena's 5-inch guns fired proximity-fused shells at the departing bombers. 2 salvos bracketed one aircraft, shredding it with shrapnel fragments. The Val plunged into the sea without its pilot ever understanding what had killed him. Word spread through the Pacific Fleet immediately. Ships that had received proximity fuses began using them in every engagement where the security restrictions allowed over-water firing. Combat results exceeded every prediction. Destroyers reported kill ratios far surpassing anything achieved with time fuses under identical conditions. The destroyer USS O'Brien, operating with Task Force 58 during the Marshall Islands campaign, achieved 12 confirmed kills during a single engagement against 18 attacking aircraft. O'Brien's 5-inch battery fired 67 rounds of proximity-fused ammunition and achieved an 18% kill rate per round fired. Under similar conditions using time fuses, historical data suggested O'Brien would have achieved perhaps 2 kills while expending her entire ammunition supply. Statistical analysis from combat actions throughout 1943 documented the effectiveness precisely. Proximity-fused 5-inch shells achieved kill rates approximately 6 times higher than time-fused shells under identical conditions. Against fast-moving targets in night engagements, the advantage increased to tenfold. Destroyers that had previously relied on volume of fire could now achieve aerial kills with dramatically reduced ammunition expenditure. The effectiveness triggered Japanese tactical adaptations that Allied intelligence observed but could not fully explain. Japanese aircraft began attacking from higher altitudes, sacrificing bombing accuracy to remain outside effective range of what they believed was improved fire control. Torpedo bombers approached at wave-top altitude, where radio reflections from the ocean surface sometimes caused premature fuse detonation. Dive bombers released ordnance at steeper angles to minimize exposure time to defensive fire that seemed impossibly accurate. These adaptations reduced Japanese strike effectiveness while failing to restore the tactical advantage they had enjoyed earlier in the war. American destroyers continued shooting down Japanese aircraft at rates that made conventional attacks increasingly costly. Admiral William Halsey credited proximity fuses with fundamentally altering the balance of power in surface engagements. Japanese aerial reconnaissance, which had previously operated with relative impunity, became hazardous as destroyer pickets achieved regular kills against high-altitude observation aircraft. Torpedo bombers, particularly effective in night attacks when visual tracking was difficult, faced radar-directed 5-inch guns, firing proximity-fused shells that detonated regardless of darkness or evasive maneuvering. By mid-1943, despite proximity fuses being used in only 25% of 5-inch ammunition expended by destroyers, they accounted for over 50% of Japanese aircraft destroyed by destroyer anti-aircraft fire. The mathematical transformation was complete. Weapons that had required perfect prediction now achieved kills through proximity detection, turning American destroyers into aerial death traps for any Japanese aircraft within range. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. October 19th, 1944, the Philippine Sea, 300 miles east of Luzon. The destroyer USS Leyte steamed at flank speed toward her assigned radar picket station, 25 miles ahead of Task Force 38. Lieutenant Commander Frederick Beckton studied the Combat Information Center plot, showing formations of Japanese aircraft assembling over Luzon airfields. Intelligence estimates suggested over 400 aircraft would attack the American fleet before sunset. Leyte carried 300 rounds of 5-inch proximity-fused ammunition, representing 3 years of American industrial innovation compressed into shells that Japanese pilots would never understand. Each round contained electronics more sophisticated than most Japanese radar installations, miniaturized into packages that could survive artillery launch forces and function flawlessly in combat conditions that destroyed conventional equipment. As the first wave of Japanese aircraft appeared on radar at a range of 60 miles, Beckton realized his single destroyer would face attacks that would have overwhelmed entire task forces just 2 years earlier. The difference was the proximity fuse, which had transformed Leyte's 5 twin 5-inch mounts from area denial weapons into precision aircraft killers. The tactical revolution extended beyond individual ship capability to fleet-wide doctrine. Admiral Mark Mitchell, commanding Task Force 58, had restructured carrier operations around destroyer effectiveness against aerial attack. Instead of keeping destroyers close to carriers for point defense, Mitchell positioned them as radar pickets 15 to 30 miles from the main force. Early detection was valuable, but the real purpose was attrition. Destroyers equipped with proximity fuses could engage attacking formations while they were still forming up, disrupting coordination and reducing numbers before aircraft reached the carriers. What had once been a desperate delaying action became systematic destruction of attacking forces. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The mathematics supported radical tactical changes. Historical data from 1942 showed that a destroyer typically achieved 1 kill per 100 rounds of 5-inch ammunition fired under favorable conditions. By 1944, destroyers equipped with proximity fuses were achieving 1 kill per 15 rounds fired, a nearly 7-fold improvement that fundamentally altered the cost-benefit calculation of aerial attacks. Japanese squadron commanders faced impossible choices. Attacking American destroyers required exposing aircraft to defensive fire that achieved kill rates approaching 10% per engagement. Avoiding destroyers meant approaching carriers through radar coverage that provided 30 minutes advance warning, allowing fighters to intercept while bombers were still climbing to attack altitude. The psychological impact on Japanese aircrews was documented through interrogations of captured pilots throughout 1944. Flight Petty Officer Saburo Sakai, the legendary Japanese ace with 64 confirmed kills, described proximity-fused anti-aircraft fire as supernatural in its accuracy. Shells seemed to explode precisely when approaching aircraft regardless of evasive maneuvering. Sakai noted that American destroyers had become more dangerous to experienced pilots than American fighters. A skilled pilot could outmaneuver a Hellcat through superior knowledge of aircraft performance. No amount of skill could evade shells that exploded automatically when close enough to cause damage. The proximity fuse removed pilot expertise from the equation, making survival dependent on luck rather than ability. Lieutenant Hiroshi Nishizawa, another elite Japanese pilot, reported similar observations. American anti-aircraft fire had evolved from predictable time bursts that could be evaded through timing and maneuvering to proximity bursts that required aircraft to remain outside effective gunnery range entirely. This forced higher altitude approaches that reduced bombing accuracy and exposed aircraft to fighter interception for longer periods. The tactical adaptation cycle accelerated throughout 1944 as Japanese commanders attempted to develop countermeasures. Coordinated attacks using multiple approach vectors were intended to overwhelm individual destroyer fire control systems. The tactic worked against time-fused ammunition, which required manual tracking of single targets. Proximity fuses eliminated the tracking requirement, allowing rapid engagement of multiple targets simultaneously. High-speed, low-altitude approaches were designed to minimize exposure, time to defensive fire. Proximity fuses proved equally effective against fast-moving targets, requiring no advanced calculation of intercept points. Low altitude actually increased fuse effectiveness by providing better radio reflection from ocean surfaces that enhanced target detection. Night attacks had previously been Japanese advantages when visual fire control was degraded. Radar-directed 5-inch guns using proximity fuses proved more effective at night than during daylight, eliminating visual distractions and providing clear radio reflection signatures against dark sky backgrounds. The Battle of the Philippine Sea, June 19 through 20th, 1944, demonstrated proximity fuse effectiveness on unprecedented scale. Japanese mobile fleet launched over 400 aircraft in coordinated strikes against Task Force 58. American destroyers positioned as radar pickets engaged attacking formations throughout 2 days of continuous action. The destroyer, USS Stockholm, operating 30 miles west of the main carrier force, faced 96 Japanese aircraft during the afternoon of June 19. Commander Ralph Earle's 5-inch battery fired 167 rounds of proximity-fused ammunition during 45 minutes of continuous engagement. Combat cameras recorded 23 confirmed kills, with an additional 15 aircraft damaged sufficiently to abort their missions. Stockholm achieved a kill rate of 13.8% per round fired, effectiveness that would have required over 2,300 rounds using conventional time fuses under similar conditions. The mathematical impossibility had become combat reality through American industrial capacity applied to a specific technical problem. The Japanese response revealed fundamental misunderstandings of what they faced. Admiral Jisaburo Ozawa, commanding the mobile fleet, attributed American anti-aircraft effectiveness to superior fire control radar integrated with improved time fuses. Japanese intelligence estimated that American destroyers had developed automated gunnery systems that calculated optimal fuse settings faster than human operators. This misunderstanding persisted throughout the war because captured proximity fuses were assumed to be advanced time mechanisms. Japanese engineers examining unexploded shells found miniature radio components but concluded they were some kind of timing device beyond their technical comprehension. The concept of radio proximity detection seemed impossible given the acceleration forces involved in gun launch. Lieutenant Commander Minoru Genda, one of Japan's most innovative tactical thinkers, analyzed American anti-aircraft effectiveness through late 1944. His classified assessment attributed destroyer success to integrated radar systems that provided targeting data directly to automatic fuse setting mechanisms. Genda estimated that American electronic fire control was approximately 5 years ahead of Japanese development. The irony was profound. Japanese forces faced technology they could not understand, partly because they underestimated American electronic capabilities. The proximity fuse represented exactly the kind of miniaturized, sophisticated electronics that Japanese military leaders believed was beyond current technology. Their disbelief became a security advantage that protected American operational secrets. October 25, 1944. Leyte Gulf, Philippines. The destroyer USS Johnston faced 17 Japanese dive bombers in the engagement that opened this narrative. Lieutenant Commander Ernest Evans had positioned his ship to screen the escort carriers of Taffy 3 from approaching Japanese surface forces. The aerial attack was secondary to the threat from 4 Japanese battleships closing from the north. But Johnston's response to aerial attack demonstrated how proximity fuses had altered destroyer doctrine. Evans did not maneuver to evade attacking aircraft. Instead, he maintained course and speed, while his 5-inch battery engaged targets with methodical precision. Each proximity-fused shell detonated at optimal range regardless of aircraft maneuvering, creating kill zones that no evasive action could avoid. The engagement lasted 12 minutes. Johnston's guns fired 47 rounds, and achieved 13 confirmed kills. The mathematical impossibility of 1941 had become routine tactical reality by 1944. American destroyers were destroying Japanese aircraft at rates that made aerial attacks unsustainable against well-defended targets. Admiral Takeo Kurita, commanding the Japanese surface force attacking Taffy 3, observed Johnston's anti-aircraft fire from the bridge of the battleship Yamato. His post-war interviews revealed that American destroyer effectiveness against aerial attack influenced his decision to withdraw from the engagement. If American destroyers could systematically destroy attacking aircraft, coordinated air-surface attacks became impossible. The strategic implications extended beyond individual engagements to campaign-level planning. Japanese naval aviation faced attrition rates that made sustained operations impossible. Experienced pilots were being systematically destroyed by defensive fire they could not effectively counter. Replacement pilots received minimal training, insufficient for the precision required to attack heavily defended targets. By November 1944, Japanese commanders were explicitly avoiding operations that exposed aircraft to American destroyer anti-aircraft fire. This eliminated most tactical options for coordinated strikes against carrier task forces. The proximity fuse had essentially neutralized Japanese naval aviation as an effective strategic weapon. The human cost of this technological advantage was substantial but asymmetric. Japanese naval aviation lost over 8,000 aircraft in combat during 1944. American combat analysis estimated that proximity fuses directly accounted for destroying approximately 1,500 of these aircraft through destroyer anti-aircraft fire. Each aircraft represented not just material loss but trained aircrew impossible to replace. Japan's pilot training programs had been reduced to provide minimum flight instruction, insufficient for combat effectiveness. The death of experienced pilots in 1943 and 1944 forced Japan to commit poorly trained replacements who fell victim to American defenses at unsustainable rates. The tactical cycle became self-reinforcing. Japanese losses forced the use of inexperienced pilots who were more vulnerable to defensive fire. Higher loss rates necessitated further reductions in training time to maintain pilot production numbers. Reduced training created even more vulnerable pilots who achieved fewer successful attacks while suffering higher casualties. December 7, 1944. Mindoro, Philippines. 3 years to the day after Pearl Harbor, the destroyer USS Lamson engaged 42 Japanese aircraft attempting to attack American landing forces. The symbolic resonance was powerful. American destroyers that had been helpless against aerial attack in 1941 were systematically destroying Japanese aircraft using technology that seemed impossible just 3 years earlier. Lamson's 5-inch battery fired 89 rounds of proximity-fused ammunition during a 37-minute engagement. Combat photography documented 19 confirmed kills with additional aircraft damaged sufficiently to abort their missions. The kill rate of 21% per round fired represented effectiveness levels that would have required over 2,000 rounds using conventional ammunition. The psychological impact on Japanese aircrew was catastrophic. Veteran pilots reported that approaching American destroyers produced physical symptoms of panic that degraded flying performance. The knowledge that defensive fire achieved kills regardless of evasive maneuvering created a sense of helplessness that broke combat effectiveness, even among experienced aircrew. Flight training instructors at Japanese naval air stations noted increasing reluctance among student pilots to practice attack approaches against simulated destroyer targets. The reputation of American destroyer anti-aircraft fire had spread through the Japanese naval aviation community, creating morale problems that affected training effectiveness. By early 1945, Japanese naval commanders were explicitly planning operations to avoid American destroyer pickets. This eliminated most options for surprise attacks and forced approaches through heavily defended corridors where fighter interception was inevitable. The proximity fuse had essentially created no-fly zones around American task forces. The broader strategic impact extended to Japanese industrial planning. Resources allocated to aircraft production were increasingly wasted when completed aircraft were destroyed faster than they could be replaced. The proximity fuse forced Japan to confront the mathematical impossibility of sustaining aerial warfare against an enemy with overwhelming technological advantages. Admiral Soemu Toyoda, commanding the combined fleet, acknowledged in classified planning documents that Japanese naval aviation had become tactically ineffective against American forces equipped with proximity-fused anti-aircraft weapons. Toyoda estimated that conventional attacks achieved insufficient results to justify the aircraft losses involved. This assessment led directly to the implementation of kamikaze tactics beginning in October 1944. If conventional attacks could not succeed against American defenses, perhaps suicide attacks might achieve sufficient damage to alter strategic calculations. The proximity fuse had forced Japan to abandon tactical aviation in favor of deliberate self-destruction. The irony was complete. Technology developed to improve defensive effectiveness had forced an enemy to adopt tactics that eliminated any possibility of tactical recovery. Japanese naval aviation committed institutional suicide, partly because proximity fuses made conventional aerial warfare impossible to sustain. The statistical evidence was overwhelming. Between January 1943 and August 1945, American destroyers equipped with proximity fuses destroyed over 3,000 Japanese aircraft through anti-aircraft fire. This represented approximately 25% of all Japanese aircraft losses during the same period, achieved by vessels that had been nearly defenseless against aerial attack at the war's beginning. The cost-effectiveness calculation was equally stark. Each proximity fuse cost $18 in mass production. The average Japanese aircraft represented an investment of approximately $50,000 in materials, manufacturing, pilot training, and support infrastructure. Every proximity-fused shell that achieved a kill returned nearly 3,000 times its cost in enemy assets destroyed. The production achievement matched the tactical success. American industry manufactured over 22 million proximity fuses during the war, representing approximately 9 billion individual electronic components produced to specifications measured in thousandths of an inch. The supply chain involved over 100 factories coordinating delivery of components from hundreds of specialized suppliers. At peak production in 1945, American electronics industry manufactured 70,000 proximity fuses daily. Each fuse contained electronics more sophisticated than most Japanese military radio equipment, mass-produced at quantities that exceeded Japanese electronic production capacity by several orders of magnitude. The technological gap had become a strategic chasm. Japanese forces faced enemies equipped with weapons that seemed impossible to develop, manufactured in quantities that defied comprehension, achieving effectiveness that made traditional tactics obsolete. The proximity fuse represented everything that made American industrial power decisive in World War II. By war's end, the transformation was complete. American destroyers that had been vulnerable escorts in 1941 had become the most effective anti-aircraft platforms in naval history. The 5-inch proximity fuse had achieved kill rates approaching 90% under optimal conditions, turning American destroyer screens into aerial death traps that no Japanese aircraft could penetrate. The Japanese never fully understood what had killed their naval aviation. Post-war interrogations revealed that most Japanese military officials believed American destroyers had developed integrated radar fire control systems that automated gunnery calculations beyond Japanese technical capability. The reality of radio proximity detection remained operationally secret until details were released in September 1945. This failure of understanding allowed the proximity fuse to remain tactically decisive throughout the war. Japanese countermeasures development focused on radar jamming and electronic warfare techniques designed to disrupt fire control systems. None of these efforts affected proximity fuses, which operated independently of external radar and required no fire control input beyond initial target designation. The human tragedy extended beyond military casualties to the broader collapse of Japanese aerial capability. Thousands of young Japanese pilots died attacking American destroyers, equipped with proximity fuses, achieving negligible tactical results. While sustaining losses that eliminated Japan's capacity for sustained aerial warfare, the proximity fuse killed not just aircraft, but the institutional knowledge required to train effective pilots. The legacy extended far beyond World War II into modern naval warfare. Every contemporary ship-based anti-aircraft system traces conceptual lineage to the Mark 32 proximity fuse, developed between 1940 and 1943. Modern weapons use solid-state electronics, microprocessors, and sophisticated signal processing, but the fundamental principle remains unchanged: detect the target automatically and detonate at optimal range. The scientific knowledge gained from developing electronics that could survive artillery acceleration became foundational for space exploration, missile guidance systems, and modern precision weapons. The engineers who solved 20,000 G-rated electronics went on to careers that established American leadership in aerospace technology throughout the Cold War. Dr. James Van Allen, who developed ruggedized vacuum tubes for proximity fuses, later designed scientific instruments for space exploration. The Explorer 1 satellite, launched in 1958, used electronics that drew directly on proximity fuse miniaturization techniques. The Van Allen radiation belts were discovered using instruments that survived rocket launch, partly because engineers had learned to make electronics survive artillery launch. The industrial legacy was equally profound. The quality control methods developed for proximity fuse mass production became standard practice throughout American manufacturing. The workforce training programs demonstrated that complex technical work could be performed by people without advanced education, given proper instruction and supervision. The supply chain management systems created to coordinate proximity fuse production supported the growth of consumer electronics markets after the war. Factories that had manufactured vacuum tubes for fuses converted to producing television tubes and radio components. Workers trained in precision assembly became the foundation for the emerging electronics industry. The proximity fuse stands alongside radar and penicillin as one of the few technologies that materially affected World War II's outcome. Unlike radar, whose development occurred in multiple countries, the proximity fuse resulted from focused American effort that combined advanced research with massive industrial capacity. The story of destroyer anti-aircraft effectiveness illustrates how technological advantages compound through sustained application. American proximity fuses did not win the war alone, but they eliminated Japanese naval aviation as an effective strategic weapon. This allowed American carrier task forces to operate with impunity throughout the Western Pacific, accelerating operations that might otherwise have required years to complete. The mathematical transformation from 0.04% kill rates to 90% effectiveness represents one of the most dramatic tactical improvements in military history. American destroyers evolved from vulnerable escorts to dominant anti-aircraft platforms through technology that enemy forces never understood and could never effectively counter. Lieutenant Commander Ernest Evans, watching Japanese aircraft disintegrate under proximity-fused fire during the Battle off Leyte Gulf, witnessed the culmination of American industrial democracy applied to warfare. Free societies had mobilized scientific talent, manufacturing capacity, and economic resources to solve a problem that authoritarian regimes had concluded was impossible. The proximity fuse proved that the greatest victories are achieved not through individual heroism or tactical brilliance, but through sustained application of superior resources guided by democratic values and scientific method. American destroyers, equipped with proximity fuses, became symbols of what free peoples could accomplish when necessity, capability, and determination aligned in pursuit of victory worthy of extraordinary effort. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.